Hello, calculus students, and welcome to another online lesson. Today we're going to continue our discussion of sign diagrams and second derivatives. We're specifically going to be focusing on sketching graphs, as well as looking at a few more problems with applications of second derivative and sign diagram. All right, so just a reminder once again, stationary points, which include maximums and minimums, as well as horizontal inflections, occur when our derivative equals 0. Anytime the derivative equals 0, that can either be at a maximum where the derivative is 0, at a minimum where the derivative is 0, derivative again meaning slope, or this thing known as a horizontal inflection where it goes up, levels out, and then continues up after that. Anytime that the derivative is greater than 0, it means we have a positive slope. Anytime the derivative is less than 0, we have negative slopes. Point of inflection occurs when the second derivative equals 0, and that's when we switch from curving down, like we would have happening here, looks like a parabola opening down, to when we switch to curving upward. So we'd have a point of inflection here, and then again here. Then we have two more inflections. One more. We curve down here, and then we switch and curve again. If we think of this as driving on the street, looking down at a car, we'd be turning our wheel to the right all the way here. Point of inflection comes, we start turning to the left. Point of inflection comes, we start turning to the right. Point of inflection comes, we start turning to the left. Notice this spot right here is both a stationary point, meaning that the slope is 0, but it's also a point of inflection. So at that specific spot, both the first derivative and the second derivative would both equal 0. Again, concave upwards, those would be places where it looks like a parabola opening up, which would be here. That's when the second derivative equals 0. And then concave downward is where the second derivative is, concave up is greater than 0, and concave downward is less than 0. So what we're going to start with is this example, an actual IB question. The diagram shown below shows a sketch of the graph y equals f prime of x between a and b. So f prime of x is slope. So it's a graph of the slopes. You input an x and you get out slopes, because it's derivative, f prime of x, all slopes. On the grid below, which has the same scale on the x-axis, draw a sketch of the graph y equals f of x. So they're giving us a graph of slope, and they want us to actually graph, the original equation, y equals f of x. Given that f of 0 equals 0, and f of x is greater than 0 for all x. So what does that mean? So at an input of 0, we have an output of 0, meaning that our graph is going to go through the origin, and all of our values are greater than, or our y values, or our output, f of x values, are greater than or equal to 0, which means we'll never go below the x-axis. We want to indicate minimums and maximums, as well as any points of inflection. Interesting. All right. So I've got some graph paper here below. The first thing they told me is that my graph is going to go through the ordered pair 0, 0, because it said f of 0 equals 0. So if I input a 0, I get out a 0 into my original function. There's a lot of ways we could start this. What I'm going to do is I'm going to make a sign diagram for this original graph. Remember, this graph here, it's inputting x's and outputting slopes, because it's the derivative graph. It's f prime. So all of these outputs here are slopes. So we start here, we have some kind of slope which is greater than 1. It's a positive slope. And the slope continues to get more positive all the way up here, because again, we're above the x-axis. So we get on here, what kind of slope do we have here? Now the initial gut reaction say, oh, we're going down, this graph must be negative. But no, because again, these are just slopes, and these are still positive slopes. Are they less positive than they were moments ago? Yes, but they're still positive until right here. What is our y value right here, or our output right here, is 0. So that means there is no slope right there, which means it must be a maximum or a minimum or a horizontal inflection. I'm going to call this point capital A. And that is my first spot where my derivative equals 0, where there's no slope. So everything up till this point, I had values that were all above the x-axis. So these must have all been positive slopes. So before A, everything's positive. Then after A, I'm getting a bunch of different y values, but you'll notice they're all negative. So after A, they're all negative slopes. Then I get to what I'm going to call point B, capital B. And after point B, all of my slopes here are all positive values. All right, so that's somewhat useful. So I know that I have two spots, A and B, where my derivative is 0, which means those are either maximums, minimums, or horizontal inflections. As we can see, we had a positive slope, which then led to a negative slope before and after A. So A must be a maximum. So A is our max. And then B, we had a negative slope, and that's going to be, and then we go after that. So B must be a minimum. All right. They also told me that my graph would never go below the x-axis. And we can see that point B, which corresponds directly to this point here on my origin on my new graph, that must be my minimum. That's my lowest point. And again, I can't go below that axis. So if I wanted to, I don't know how high to go, but I know that A is my relative maximum. So I'm just going to plot a point right in line, draw a little dotted line here, right in line with that. And this is going to become my maximum. This is going to become my minimum. And what else can we do here? So on the original graph, we can look at the slopes of that. The slope of the slope is our second derivative. And anytime the slope of the slope equals 0, we know that's a point of inflection. So we have a point of inflection right here, and we have a point of inflection right here. That's where we're going to change directions. All right. So I'm going to just pick a random place to start. Again, directly in line with A. Have to be above the x-axis, it says. And again, what kind of slope do we have all in this section? Well, they're all positives, but they're getting more and more steep as I go along. So I start off with a positive slope, but it's getting more and more steep until it gets right to this spot right here. And then it's still positive, but it's less positive. So we're getting less and less steep until we get to A, in which case we flatten out. Now, from A, which is my maximum, all the way through this next bit, it's all negative. But you'll notice it gets more and more negative until right here, which is a point of inflection, and then it will become less and less negative until it hits B, in which case the slope will become positive. So we're getting more and more negative until right here. And then from that point, we're still negative, but we're getting less and less negative with our slopes until we hit our minimum. And then last but not least, we have positive slopes that are getting more and more positive. Again, higher and higher and higher and higher slopes. So to start with, it's low, like 1, and then 2, and then 3, and then 4. So getting steeper and steeper and steeper as we go along up until about B. I may have gone just a smidge too far, so let me fix that. Something along those lines. That is converting a derivative graph into an original function graph. You may want to replay that and watch that a couple times or try it on your own. We'll look at some more examples like this next class. Now let's go to some regular applications of derivative and second derivative. Particle P moves in a straight line with a position relative to the origin O given by S sub t, S of t equals 2t cubed minus 9t squared plus 12t minus 5 centimeters, where t is the time in seconds, and t must be greater than 0, greater than or equal to 0. So time is only positive in this case. Find an expression for the particle's velocity and acceleration. Draw sign diagrams for each of them. So similar to the problem that we did last time, we're going to do S prime of t, which will represent our first derivative, also known as our velocity. And we end up with 6t squared minus 18t plus 12. Now we're going to do a second derivative, which gives us 12t minus 18. Make a sign diagram for each one. Well, to make a sign diagram, the first thing we need to do is we need to set our derivatives equal to 0. So if I do 6t squared minus 18t plus 12 equals 0. First, you'll notice that I could factor out a 6 from everything, leaving with t squared minus 3t plus 2 equals 0. You could use the quadratic formula, but I think we can factor this pretty easily. We have t equals 0. We need something that multiplies to be 2, but adds to be negative 3. So they must both be negative in order to multiply to a positive and add to a negative, and 1 and 2 gets the job done. If we set each of those factors equal to 0, we can see that t equals positive 1 and positive 2. So when we make our sign diagram for our first derivative, we're going to have a 1 and a 2 here. Now we just need to check what happens when t is less than 1. Well, a great number that's less than 1 is 0. If I plug a 0 into the original function, 0 here, these cancel out, and then I'm just left with 12. So that is a positive number. So before 1, it's positive. Between 1 and 2, I could plug a number like 1.5 in, and I'm going to use a calculator to help me do this a little bit faster. But if I take 6 times 1.5 squared, I end up with 13.5. And then I'm going to do negative 18 times 1.5. I get negative 27. And then I have 12. 12 plus 13.5 is 25.5, and 25.5 is less than the absolute value of negative 27. So there's more negatives than positives. So this is negative, as we may have guessed anyway. And then last but not least, we need a number that is bigger than 2. I'm going to pick 10. So I would have 10 squared right here, which is 100. 100 times 6 is 600. 600 minus 18 times 10, which is 180. It's going to be very positive. Plus 12 more is still very positive. So that is our sign diagram for the first derivative. For the second derivative, I'm going to do my work over here. I set 12t minus 18 equal to 0. Add 18 to both sides. I get 12t equals 18. Divide both sides by 12, and I get 1.5 or 3 halves. So I plot that on a number line. This is my second derivative here. Check a value that's greater than 3 halves, like plugging in, I don't know, a billion. 12 times a billion right here would give me 12 billion minus 18 is still very, very positive. And then if I put in something like negative a billion, 12 times negative a billion would be very negative, minus a few more would still be extremely negative. So that's a check for that one. All right, we've got our sign diagrams. Find the initial conditions. Initial conditions are happening right at the beginning of our problem, when t equals 0. So at t equals 0, we have a, well, just looking at the sign diagrams, we can see that we have a positive velocity, but we have a negative acceleration. And so those are our initial conditions. If we want to be more specific, we can say, we can actually plug in our values of 0. And we've already done that once. So if I plug in 0 into my original function, I got a positive 12. So that is velocity, which is meters per second. Or sometimes you'll see that written as 12 meters second to the negative 1 power, which we know means divide by seconds. So again, meters per second. What's happening with our acceleration? Well, if I plug in a 0 over here, the 12 cancels out, and I'm left with negative 18. So I have a negative acceleration, which means I'm slowing down, which is negative 18 meters per second squared is acceleration, or meters per second to the negative 2. Now describe the motion of the particle at t equals 2 seconds. Well, once again, at 2, that was one spot where we saw that our derivative was 0, which means the velocity is 0. So we're going 0 meters per second. And what else do we have? We have our acceleration, which at 2, we know it's a positive acceleration because it's greater than 3 halves. If we plug it in, we have 2 times 12, which is 24, minus the 18, which gives me positive 6 meters per second squared. Find, oh, and all these should have been centimeters. I apologize. So centimeters here, all throughout. Find the time and positions where the particle changes directions. All right, so changing directions, that would be where I go from forward velocity to backwards velocity and then back again. So those times would include t equals 1 and t equals 2. Now, how do I get position? Well, the first derivative gives me velocity, which is like my speed. The second derivative tells me my change in my speed, also known as acceleration. So where do I get position? That is the original function right here. So I take, put a 1 in there. 1 cubed is 1, so it's 2 minus 9 plus 12, which is 5 minus 5, 0. Okay, so we are at 1, or I'm sorry, 1 is my time, and my position is 0 meters for that first one, which goes over here. And then for my second one, I plug in a 2. What do we have? Plug in a 2 here, we get 8 times 2, which is 16. Plug in a 2 here, we get negative 36. Plug in a 2 here, we get positive 24 minus the 5. So use my calculator, 16 minus 36, which is negative 20, plus 24 minus 5. Gives me negative 1. I did that correct. So negative 1 meters. So we've moved back 1 meter at t equals 2. So those are the times and positions of where I was. Again, these should all be centimeters. Last but not least, determine the time intervals when the speed is increasing. Speed is increasing when t is greater than 3/2 seconds. How do I know that? Because right here is where I switched from decreasing in my speed to increasing my speed. All right, applications. One more problem, and it'll be very quick. X-coordinate of the point of inflection on the following graph. X-coordinate of the point of inflection. Well, point of inflection we find from our second derivative setting it equal to 0. So we need to do our first and second derivative, set it equal to 0, and solve for x. So our first derivative, it's product rule. We have a u equals x, a v which equals e to the x. Derivatives don't get much nicer than this. So our derivative of x is 1. Our derivative of v is e to the x. So I put those together with 1 times my e to the x, which is just e to the x, plus my x times e to the x, which is x e to the x. Now I need to do the second derivative. And I have e to the x as my first term, and the derivative of that is just e to the x. Now I end up having this term, which is the same as my original problem. So since I knew the derivative of the original problem turned into this stuff, why don't I just do the same thing here, bring this down. So it's e to the x plus x e to the x. Again, we're just doing product rule again for the same u and v. Now let's simplify this. I have e to the x plus another e to the x, so that's 2 e to the x plus x e to the x. And you'll notice that both of these have an e to the x in them, so I factor out an e to the x. I am left with 2 plus x. We want to set each of those equal to 0. So I could say e to the x equals 0. Well, that's an impossible thing. There's no exponent that will turn in e into a 0. Even a 0 exponent makes it 1. So that means that I have to set the other equal to 0. 2 plus x equals 0. Subtract 2 from both sides, and I get x equals negative 2. So the point of inflection, or the x value of the point of inflection, is x equals negative 2. So I didn't really do much new in this video, a lot of the same sorts of things, but the graphing was a sort of a new approach to it, and looking at a graph of derivatives and trying to get our minds around that. It's one of the crazier things that we have to do in this class. The other problems were a little bit more direct application, especially that last one. So I've got a few book problems. I kind of recommend that you take a look at some of these to get a little more practice with this, and we'll do some practice with curve sketching in class next time. Until then.